Professor Rongrong Wang to give us this talk. And first, I would like to very briefly introduce her. Dr. Rongrong Wang is associate professor at Michigan State University with a joint appointment in the Department of Computational Mathematics, Science and Engineering, and the Department of Mathematics. And she received her PhD from the University of Maryland, College Park, and then did a postdoc position at University of British Columbia. Her is interested in modeling and optimization for data-driven computation, developing learning algorithms, optimization formulations, and scalable numerical methods with theoretical guarantees. And her work has applications in signal processing, machine learning, and inverse problems. And today, she will give us a talk on the PAC-Bayes optimization for neural networks. Okay, that's all for my introduction. So, Rongrong, can you? So I will.
Yeah.
Uh,
Thank you for the invitation and the nice introduction. Today I'll be presenting our work that focused on integrating the PAC-Bayes theory into learning training of neural networks to improve the generalization. This is joint work with 3 of my PhD students, Xitong Zhang, Aljit Ghosh, and Guangliang Liu, and has been published in these 2 previous conference papers. So let's begin with the supervised learning setup. Under the assumption that the training and the testing data sets are RID samples from the same underlying distribution, we define the training loss to be the empirical mean of the loss on each training sample, denoted by L theta S, where S is the training set with the size M. And the expectation of the training loss is defined to be the population loss or generalization loss, sometimes also called population or generalization error. Our goal is to find the optimal parameter theta that minimize this population loss. However, since we only have the training data, we want to make sure the model trained on the training data also have a small generalization error. So in practice, this generalization error is empirically estimated using the test data set. So we deem the testing error as a good proxy of the generalization error. So what are the common ways to improve generalization? Broadly speaking, there are 3 main approaches: acquiring more high-quality data, designing better model architecture, and improving the training, the optimization during training to enhance generalization. And we are going to focus on the third one in this talk. When we talk about optimization, it's worth noting that in the past, most research focused on proving the convergence and analyzing the convergence rate of the algorithms. That made a lot of sense because in the pre-deep learning era, when models were typically simple, like linear regression, we usually have convex risk functions. So for convex problem, all algorithms converge to the same minimizer. So the only thing that really matters is how fast you can get there. But in the deep neural network setting, things are very different. Due to the overparameterization, the optimization landscape becomes highly non-convex with many local minima. In this setting, not only the choice of the optimization algorithm matters, but even the initialization points have a huge impact on the final result. So this shift gives rise to a new line of research around generalization. Rather than asking which algorithm converge fastest, we now ask which optimization method lead to models that generalize better. By the way, feel free to ask questions in the middle. To study generalization more rigorously, researchers have proposed various mathematical formulations to quantify it, leading to a range of generalization-related measures. One popular such measure is called sharpness. The intuition behind sharpness is that these flat minimizers, where the loss surface has low curvature, tend to generalize better. Why? Because we can think of the testing data as a slight perturbation of the training data. If a model lands in a region of the loss surface where small perturbation don't cause very large change in the loss, like this one, then it's more likely to perform well on unseen data. So sharpness attempt to capture how robust the loss is to perturbation around this minimizer. This provides some useful intuition into generalization. However, it is somewhat crude and non-quantitative and don't always give us a complete picture. From a classical perspective, when there are many minimizers that can fit the training data, it means we are in the overparameterized regime of this model complexity trade-off picture. In this setting, regularization plays a crucial role in training neural networks. Otherwise, we'd expect to see overfitting and poor generalization rather than the strong performance that deep networks actually achieve. So the modern study of generalization is deeply tied to the understanding of regularization. That's the direction most research is taking. Now let's take a brief look at the different forms of regularization. In deep learning, regularization is formally defined in this paper as any supplementary technique that can enhance the generalization. This is a widely accepted definition, but I think it's a little bit vague. So a more precise definition is that regularization is any technique that reduces the hypothesis space, which is the set of models considered during training. In the context of neural network training, each instantiation of neural network represents a hypothesis. And the collection of all such hypotheses form the hypothesis space. And the goal is to learn to identify within this space the model that best explain the observed data. Since optimizing over a very large hypothesis space is highly challenging, we rely on regularization technique to reduce the search space to a manageable subset. This technique can be characterized as either explicit or implicit regularization. Explicit regularization involves deliberately adding penalties, constraints, or modifications to the optimization procedures in order to shrink the hypothesis space. Common examples include weight decay, dropouts, stochastic depths, etc. Weight decay is like adding large weight penalties, and these two are imposing architectural changes or changing the dynamics of training. However, as demonstrated in this paper through many experiments, the author concludes that while explicit regularization can improve performance, it is neither necessary or sufficient for achieving good generalization. In simple words, what the author is trying to say is that even without explicit regularization, the performance of the neural network is still fine. And the reason is the existence of implicit regularization. So implicit regularization refers to the effects that arise naturally from the choice of an optimization algorithm or training setups without explicitly adding regularization terms or constraint to the loss function. Examples include small batch size, batch normalization, large learning rates, high momentum, noise injection, and even the choice of optimizer itself. These forms regularization are often more subtle and easy to overlook, and they are difficult to be disabled. For instance, using any positive learning rate would inherently impose an implicit regularization effect. Setting the learning rate to 0 would halt the training entirely, so making it impossible to isolate this impact. Despite being less obvious, implicit regulation often play a crucial role, and sometimes even a dominant role in shaping the generalization behavior in neural networks. Using ResNet 18 trained on CEPA-10 dataset as an example, we analyzed the impact of various regularization techniques on the final test accuracy. The baseline accuracy is approximately 91% without data augmentation, and around 15 of this performance gain can be attributed to the combined effect of this regularization method. Among them, the learning rate has the most significant impact. Using a large learning rate versus a small one lead to 5% difference in the accuracy. This is followed by the effect of batch size, weight decay, batch normalization, and noise injection. Additionally, using the SGD algorithm gives about 3% higher accuracy compared to using add-on. So with this level of difference, hyperparameter tuning definitely seems worth it. But there are two main challenges. One is the time it takes to do the training, the tuning. And the other is that we still don't fully understand how these regularization techniques interact with each other, how exactly they affect generalization. We don't know if we really need all of them or just a subset of them is enough. And some of them might even conflict with each other. For example, the dropout, noise injection, and small batch size. These three all regularize the model by adding some kind of noise or randomness during training. A lot of work has tried to study the effect of one regularization method at a time while keeping the others fixed. We also start out doing that, but we quickly realized that it doesn't give us the full picture and also does not help us to quantify the generalization in a rigorous way. So that's what led us to consider to take a more thorough look and look at the quantitative measures of generalization like the PAC-Bayes bound. Here is the motivation for using the PAC-Bayes bound. So given the previous considerations, we ask, can the PAC-Bayes theory help us to explain or even improve generalization in a more systematic way? The PAC-Bayes bound gives us a theoretical bound on the generalization error. It is expressed in terms of prior and posterior distribution of the models. It is originally developed to explain the so-called Bayesian inference, which I will talk about in a minute. But the tools actually turn out to be much more broadly applicable. So the PAC-Bayes bound applies to any algorithm that output a distribution over hypothesis space, not just a single model. Recall that our goal is to mathematically characterize the generalization, which means we want to find a bound that can upper bounds the generalization error in terms of quantities that we can compute from the training data. And we don't just want any bound, we want it to be as tight as possible, so it can reliably reflect how well the generation is. Now, among all the generation bounds we have been established so far, why do we focus on the PAC-Bayes bound? The short answer is so far, this is the tightest for medium to high complexity models like neural networks. So let's start with something simple, the PAC bound, the PAC bound. Unlike PAC-Bayes bound, which deal with distribution over hypothesis, the PAC bound is defined for a single hypothesis, H. You can think of this H as a one-trained neural network. So here we denote the hypothesis space as big H, and the small h is a member in it. On the left side of the inequality, we have the generation error. And on the right, we have the training error plus the a term that scales with the square root of the log of the size of the hypothesis set and that of the inverse of the failure rate, delta, and divided by the number of training samples, m. This square root term captures the discrepancy between the training and generation loss. It tells us that minimizing the training error alone isn't enough. We also need a small hypothesis space and also a large training set for this bound to be small. But here is a problem. This bound become vehicles when the size of the hypothesis space become infinity, which is exactly what happens when we train a neural network. So we need a refinement. One refinement is using the VC dimension instead of the cardinality of the set. This gives us a very similar bound now in terms of the VC dimension of the hypothesis set H. This is a nice improvement, but in practice, the VC dimension of neural networks can be huge. And what make it worse is that this VC dimension appear outside the logarithm, so the bound can be still extremely loose. A further refinement comes from using the Rademacher complexity, which is a fine-grained complexity measure. More specifically, it is data dependent. This is a big advantage by making it data dependent because it means the bound doesn't need to hold uniformly for all the data set. It only needs to hold for the current data set where the Rademacher complexity is computed on. This makes this bound much smaller. And indeed, modern generalization results for neural network are mostly derived using this bound. However, these bounds are only tied asymptotically, and in practice, their numerical value can still be much larger than the true generalization error that is estimated from the data. So while useful theoretically, these bounds are not very tight, are not tight enough to be practical. This brings us to the PAC-Bayes bound, which is the most sophisticated one. This bound is not only data dependent, but it's more flexible than that. It also depends on the prior and the posterior distribution. So this bound involves a KL term between the prior and posterior distribution over the hypothesis, and it holds for any posterior given a prior with high probability. Because it depends on the specific choice of prior and posterior, it doesn't have to hold uniformly for all models or all data sets, which give us more flexibility to make it tighter in practice by choosing good priors, for example. And indeed, the bounds are empirically much tighter than other bounds we've discussed. If some of you are not familiar with the language of Bayesian inference, let me briefly go over the important concept in it. So the prior refers to your belief in a hypothesis H before seeing the data. And this term is a likelihood that shows how likely the observed data S is, assuming your model H is true. And evidence is the total probability of seeing the data you see, considering all the hypotheses. And posterior is your updated belief of the model H after seeing the data S. And this Bayes rule gave us a principled way of calculating the posterior based on the prior and the data. But in practice, there are many other ways to acquire the posterior distribution, not necessarily using the Bayes rule. So in general, Bayesian inference include any algorithm that is consists of these procedures. One, we start with choosing a prior distribution. We observe some data, and then we evaluate how surprising the data is under different hypotheses, and use some update rule to produce a posterior distribution, Q. And then the algorithm outputs the posterior distribution, which is our final output. Because PAC-Bayes bound was designed to explain the result of the Bayesian inference from a generalization perspective. So the posterior distribution inside this bound can be anything, since there are many ways to define the updated role in Bayesian inference. Looking at this bound, it is probabilistic bound. It holds with probability 1 minus delta, and it holds universally for all possible posterior distributions as long as the prior P is fixed in advance and doesn't depend on the training data. This means that you can use this bound to optimize over Q. And in this bounds, we can see that in order for the bound to be small, we not only need a small training loss, we also need a bounded data set because this theorem requires the loss, the bounded loss function. This theorem requires the loss to be bounded. And we also need a good choice of the prior distribution, meaning that this choice of prior enable the existence of some posterior distribution that can guarantee the KL term to be small and simultaneously make the training loss term to be small. And in addition, we also need a large training set so that this in the denominator is large. So altogether, this PAC-Bayes framework gives us a way to reason about generalization in a flexible but still quantitative way. There's already some promising evidence that the PAC-Bayes bound can capture generalization very effectively. For example, in this previous paper, the authors trained over 10,000 models on two popular datasets, CEPA-10 and SVHN, and compared 40 different complexity measures in terms of how well they correlate with the actual generalization performance. And among these, 4 PAC-Bayes measures were shown, which I've highlighted in the red box here. What they found is quite interesting. PAC-Bayes measures had the strongest correlation with the actual generalization, outperforming other popular complexity measures like the Frobenius norm and PAS norm. In this chart, a perfect correlation is indicated by a value 1. So the closer these numbers are to 1, the better the complexity measure reflects generalization. Each row corresponding to a different complexity measure. Due to the space limitation, I've just included the top part of the table here. The column corresponding to different ways the model generalization varies. For example, we can vary the learning rates, and for each learning rate, we train a different model, and then we compute the PAC-Bayes bound for each one, and then compare those ranking to the actual test performance to see how well they correlated. Ideally, a good complexity measure should produce ranking very close to the true generalization ranking, making this correlation to be 1. And while we can see PAC-Bayes rows clearly outperform others, many values in these rows are still far from 1, and some are even negative. So the key takeaway here is PAC-Bayes gave us a much better signal than other measures, but there's still room for improvement. So we either want to get tighter PAC-Bayes bound or potentially find new approaches to go even further. So although the PAC-Bayes bound is quite promising, the traditional way of implementing it is not very efficient. Traditionally, it has mostly been used after training, not during. It means that it is only used to evaluate generalization, but not necessarily improve it during training. And there are a couple of other limitations. First, the classical theory assumed the loss function to be bounded. It ruled out many popular laws, like the CE laws. Second, the prior distribution in the bound is usually required to be fixed ahead of time and should be independent of the data. But in practice, we don't have a good way to choose the prior, and this choice can significantly affect the tightness of the bound. So here is what we propose. Our goal is to refine the PAC-Bayes training and show that it has the potential to compete with standard training methods like SGD or ADAM with regularization. We are not the first to apply the PAC-Bayes training, but previous approach have generally fall short in performance compared to the classical optimization techniques. So to address this, we develop a version of PAC-based bound that work well with unbounded loss function. It's a key limitation in previous work. While some prior PAC-based bound for unbounded loss also exist, they tend to be very loose and not practically very useful. Briefly speaking, in our approach, we would like to directly optimize the PAC-based upper bound during training to reduce the generalization error. This is conceptually very similar to how the diffusion model are trained, where instead of maximizing the true likelihood, in diffusion model, they maximize the elbow bound. Likewise, we want to maximize this generalization bound instead of directly minimizing the generalization error. Here is the new bound we derived. As you can see, it is clearly still a PAC-based type. And we have this familiar KL term in it, and also in the denominator, we have the number of samples. Now the main difference is this K lambda term. In the bounded loss setting, this would be the hard bound of the loss function. But since we're dealing with unbounded loss, we define this K lambda as some sort of exponential moment bound instead, which make the analysis a little bit more subtle. To give you some intuition, look at this inequality that define K. The model here is probabilistic. It is drawn from the some prior distribution parameterized by lambda. Because the model is probabilistic, this training loss is a random quantity. And this is the expectation of the training loss. So we have e to x minus ex essentially on the left. And on the right, we have e to gamma square k. So this is very similar to the definition of sub-Gaussian bound, as you can see, except that this is one-sided. And this one-sidedness make this bound significantly weaker than the sub-Gaussian norm. So surprisingly, these bounds for many common useful loss functions, including the cross-entropy loss, we can show that the existence of this bound K can be guaranteed as long as the second order moments of this random variable exist, which is a very mild assumption. And now looking at this parameter lambda here, this is a parameter for the prior distribution. For each given lambda, we have a different, we have a fixed prior distribution and a corresponding exponential moment bound K. So this exponential moment bound is a function of the parameter of the prior function. And we can calculate such K lambda from this inequality and the training data in advance. And once we obtain the K lambda, we insert it into the PAC-based bound for the later training. So in summary, our algorithm consists of two steps. First, we use a Monte Carlo estimator and this equality to estimate the K, and then we plug it into the PAC-based bound and optimize the model by minimizing the bound. So in order to do the actual coding, we first need to derive a closed form expression of the KL divergence term. For that, we parameterize both the prior and the posterior as Gaussian distributions. This isn't the only possible choice, but it's a natural one. The prior is centered at the initial weight theta 0, which we chose to be the chi-mean initialization of the network, and has trainable variance. The posterior is centered at the current model weight data and has its own trainable variance, sigma. This means we are learning both the mean and the variance of each weight of the neural network. Let's see how a forward path look like for this stochastic neural network. This is a simple example, consists of a one-layer neural network with a two-dimensional input. For each layer, the weights are sampled from Gaussian distribution. The input is deterministic. To sample the weights, we first sample them from the standard normal distribution and then scale it by the variance and shift it by the mean. this sample weight is used in the forward pass, and then we can repeat this procedure many times in order to calculate the expectation over the posterior distribution. This allows us to calculate the first term in the PAC loss. And for the second term, the KL divergence has a closed form expression under the assumption of two Gaussians. And we can see that this term is just a function in terms of the mean and the variance of the prior and the posterior distribution. And the third term, K, as explained before, has been calculated in advance using that inequality of exponential moment bound using and the training data. So everything in this bound is known up to now. So we can start to optimize the parameters inside this function using gradient descent type of method. So inside the gradient descent, we are updating four variables: the mean of the posterior, the variance of the posterior, the variance of the prior, and the tilt parameter gamma involved in estimating the exponential moment bound. So this is the training algorithm, which is essentially nothing but trying to minimize the PAC-Bayes bound. And we provide some justification for the final minimizer. On the left, we have the generalization error of the learned model by the PAC-based learning. And on the right, we have the minimum value of the PAC-based objective plus a very small additional term. This result tells us that minimizing this PAC-based bound during training guarantees low generalization error up to a small residue. In other words, optimizing its bound is not just heuristic, it's theoretically grounded. This is our final algorithm. To be honest, there's one key limitation we encountered, which is the PAC-based training often doesn't reach full convergence, especially on more complex models. In many cases, we'll see that the training accuracy plateau around 90%, and it cannot go much further. We suspect that this is because the PAC-based bound we derive is still not tight enough in these settings, which limit how far the model can improve. So in practice, we use the PAC-based training as stage 1 and then follow it with a stage 2 of standard SGD training. But there's an important difference. In this stage 2, we use automatically learned noise level from stage 1, and then we don't use any weight decay or any other explicit regularization, making this phase also tuning free. Of course, we can plug in a strong optimizer for stage 2 like SAM to push the performance further. But our goal here is to see how good the result can be without any manual tuning. And of course, there are still a few hyperparameters involved, like this gamma 1, gamma 2, number of epochs, learning rates, right? We still need to choose the learning rate and batch size. But we will show that the final performance of this algorithm is much less sensitive to this choice of the parameters. That's because fundamentally the PAC-based bound itself already capture most of the regularization effect, so we no longer need to rely on careful tuning of things. Now let's look at some numerical results of the PAC-based training. In the first experiment, we compare with our method with previous method, also on PAC-based training. So these baselines are either established for bounded loss or unbounded loss. The first four are for bounded loss. So because we are using cross-entropy loss in our experiments, we need to add various heuristic modifications to them in order for them to adapt to the unbounded loss. And we follow this paper to add the heuristics. And these are the results obtained when training Cypher-10 on this small to medium-sized neural networks. And there are also PSA-based bounds for unbounded loss in the literature, but these have almost mostly remained theoretical and until now have not been used in actual training. So in this experiment, we take those existing bound and plug them into our training pipeline, replacing our own bound, but keep everything else exactly the same. We can see that just by using our bound, we can get an improved final performance by several percentage points compared to all previous methods. This figure provides some additional details about the previous experiment. We compare our method with that two existing bound for unbounded loss and track how the model performed during training. In the plot, this layer refers to our method where the prior distribution is parameterized with layer-wise constant variance. That means all weights within the same layer share the same variance. Looking at this right-hand figure, we can see that these two existing PAC-Bayes bounds are extremely large during training, making them not informative. And in this left figure, we can see the model trained by minimizing this existing bound perform very poorly with very low test accuracy. And in contrast, our method gave much tighter bound and much higher accuracy. Okay, in this experiment, we compare a single run of our PAC-Bayes training versus optimally tuned SGD and ADAM. So this figure shows that remarkably, a single run of the SGD of our PAC-Bayes training can nearly match the best performance of SGD and ADAM, even when those are optimally tuned. There are two versions of PAC-Bayes training, scalar and layer. Scalar is when the prior has a constant variance across all layers, and layer is when the prior has a layer-wise constant variance. Both versions are tuning-free. In contrast, SGD ADAM and ADAM W require careful hyperparameter tuning. We mark their test accuracy across various hyperparameter settings using the stars, triangles, and crosses. As you can see that the accuracy ranges widely from as low as 75% to over 90%. These four figures show similar results for four different models, where the PAC-Bayes result constantly rank among the top performing runs, even compared to the best tuned SGD and ADAM variants. This figure shows the same result hold for CIFAR 100 dataset. Here we test the sensitivity of our method to the common implicit regularization parameters. At the beginning of the talk, I mentioned that on CIFAR 10, batch size can affect the performance of SGD by 2%. Actually, on CIFAR 100, it can affect the performance even more by about 7%. In contrast, the PAC-Bayes one are barely affected by the change of the batch size. And the same thing happens if we use the ResNet 34 dataset network. Next, we show the PAC-Bayes translation. As PAC-Bayes training is also insensitive to other implicit regularization parameters like the learning rates, the momentum, and is also quite stable with respect to the PAC-specific parameters gamma 1 and gamma 2. You can see that the results is almost unchanged, no matter how we change these parameters. This figure demonstrates the performance still hold if we use graph neural networks. We have used the standard standard benchmark dataset for GANs. And for GANs, Adam W is the state-of-art optimizer. And we use the optimal hyperparameter tuning for Adam W and obtain this result in the table. And we observe that the result of Adam W with optimal tuning is similar to a single run of our PAC-Bayes training, which again require no tuning. And we observe additional benefit here is that because many graph processing dataset include validation datasets that's specifically used for hyperparameter tuning. Since our method doesn't require tuning, we can simply combine the validation dataset into the training dataset, which allow us to train our model on more labeled data and often result in a performance boost of several percent. Finally, we apply our method to the large language models, specifically the BERT and the GPT-2 model, and compare it with baselines on 5 different benchmarks. And we can see that surprisingly, the result is even more encouraging in this case because it outperformed all the baselines for these tasks. What's especially interesting is that the PAC-Bayes bound doesn't break down as the model size increase or as the model to data ratio grows, which is often the case with LLMs. This is a bit surprising to me because we would typically expect the KL term divided by the number of training samples to become large in the overparameterized settings. But in practice, the bound remains very stable and the generalization remains strong. It suggests the PAC-based training can stably scale to large models, but it also raises new question. Why doesn't the bound explode, as theory might predict? So further investigation is definitely needed to understand what's going on under the hood in these highly overparameterized regimes. Finally, I want to show you the generalization gap. In these plots, we are tracking the training accuracy versus the test accuracy throughout the course of training. In the ideal case, when the generalization gap is 0, the training and testing accuracy should match. So the point that lies on the diagonal line y equal to x corresponding to perfect generalization. And the closer the point are to this line, the better the generalization. If the points fall below the line, it means the model is overfitting. The test performance lags behind the training performance. In the figure 1, we plot 3 curves. The red one is the PAC-Bayes training stage 1, which means we are minimizing the PAC-Bayes bound directly. Gray is for PAC-Bayes training stage 2, is the supplementary SGD phase. Blue is the normal SGD training with optimally tuned hyperparameter. What's interesting is that stage 1 of PAC achieve almost perfect generalization because the red point lies very close to the y equal to x line. However, the stage 2, which we added to improve optimization, actually perform worse and pulls the performance back down to the level of standard SGD. In this figure 2, we show that PAC-based training under different hyperparameter settings. As you can see that the results are very stable. There's minimal variation, indicating the method is not sensitive to tuning. And in the figure 3, we show the same plot, except it's for SGD training under different hyperparameters. So here you can see that the results are much more sensitive. And even the best SGD result, which is the blue one, this is the same line as this one, is worse than stage 1 of the PAC-based training in terms of generalization. So this picture gives us a clear takeaway, which is PAC-based training not only improves generalization, but it does so constantly across different hyperparameter settings. Here concludes the talk. In this talk, we describe a new PAC-based training framework, and we demonstrate the potential of such training not only in terms of matching the performance of the optimally tuned classical training method, but also reducing the need for the expensive tuning. One major advantage is that the PAC-based training is insensitive to the large batch size, which means we can use very large batches to speed up the convergence, especially as the GPU memory become more affordable in the future. It also reduces the reliance on cross-validation. That said, there are still some limitations. The PAC-based bound itself has room for improvement, And we saw that stage 2 for training doesn't always preserve the excellent generalization from stage 1. There's also memory overhead from learning and storing the posterior variance, and also the per iteration cost is higher. Looking ahead in the future, we want to explore ways to tighten the PAC-Bayes bounds and improve the stage 2 training and reduce the computational overhead. Let's conclude my talk. I'd like to take any questions that you may have. Thank you.
Thank you, Rongrong, for the great talk.